Okay, so the goal for today is to get ourselves to the point that we don't need to draw the pictures, but that we do have some awareness what the chemical equations and chemical reactions are representing. We're essentially making this little journey right here. We started our chem study experience at the macroscopic level, like looking at demonstrations and experiments. And then you learn to draw kind of a particle level picture of things. And then we incorporated this rule that says you have to have the same number and same type of particle on both sides of your picture. And now today, we're going to turn that into chemistry's symbolic representation of this situation, which is balanced chemical equations. We've even kind of learned how to read chemical equations. So we've learned that if we look at this, our interpretation is that this is telling us one particle of magnesium reacts with two particles of HCl. And notice that I've drawn them so they're not touching one another, so they actually represent separate little entities. And that is going to form a particle of MgCl, or MgCl2, and a particle of H2. So we've kind of learned to read these things along the way. And today we're going to kind of formalize how this all works. This little arrow right here, right there, I don't want you to use an equal sign. So when you're balancing equations, when you're writing equations, I expect to see the arrow, not an equal sign. And if you need a verb to go with it, since I won't let you say equals, you can have something like yields, or even reacts to form. Something like that would be more appropriate than equals. These two things don't equal one another any more than a pile of butter, eggs, and brown sugar and a bag of chocolate chips equals a chocolate chip cookie. If you walk into the kitchen and say, hey, Mom, can I have a chocolate chip cookie, please? And your mom lays out the butter, the brown sugar, the eggs, and the chocolate chips in front of you and says, here you go. That doesn't equal chocolate chip cookie. With a little bit of effort, that could yield chocolate chip cookie, but it most definitely isn't the same thing as chocolate chip cookie. This is not the same thing as the other side of the reaction, but these things will yield these other things. So the verb we need is yields, not equals. When we look at this, the reactants are at the tail of the arrow. Reactants turn into products. And it's typically written left to right, but you will occasionally see where they have it flipped around and they have the arrow going the other direction. So we're looking more at a tip of the arrow, tail of the arrow type situation. And then within these chemical reactions, you're going to see some little things in parentheses here. And those represent the physical states. It's telling you something about what it looked like so that when you need to represent this with a picture, you know what it is that you need to draw. Most of these are fairly obvious. S is solid, L is liquid, G is gas. We've actually already run into aqueous. Aqueous is dissolved in water. Or sometimes you'll see it written as a solution of. So up here we might say reacts to form a solution of magnesium chloride. So these are the symbolic representations of the physical states. We have learned to use particle level representations of the physical states. And so these little symbols are going to help us know what to draw. If it's a solid, we know that that's the situation where we have to use some edges to say this is a solid blob of something. Now, I'm going to use just a generic compound here to make all of our drawings. My compound is going to be pink blue. There we go. So we have the solid pink blue. Pink blue could be in its liquid state. And if we wanted to show pink blue in a liquid state, we would put it in a container, because we keep liquids in a container. We've learned to use the Pictionary representation of these little waves to show us that we've got some kind of a liquid in our container. And liquids are a little less structured than solids, so we might draw pink blue with a little less organization to it. Okay. So there's kind of a more chaotic version of pink blue. Okay, will do? Yep, okay. Okay, pink blue could be a gas. If it's a gas, we know it's going to be just kind of scattered everywhere. The particles are going to be very far apart, unlike the solid state and the liquid state. Gas particles are really, really far apart. Solids and liquids have pretty similar densities. Gases have a substantially smaller density. Or pink blue could be aqueous. Now, aqueous pink blue, I'm going to actually put the aqueous down here a little bit because we have to draw a couple different possibilities. If pink blue is aqueous, before we can draw it, we have to decide, is pink blue molecular or is pink blue ionic? So aqueous means it's been dissolved in water. So remember, those little arrow things are representing our water molecules. If pink blue is molecular, then dissolving it in water simply means that the pink blue particles are going to mix and mingle with the water particles, but they're going to hold together. So there's some pink blue particles stirred in with some water particles. But if pink blue happens to be ionic, it's going to separate into its pinks and its blues. And maybe to show that they're separate, we should have a few more water molecules here, now that we know where everything's going to be. And if it's ionic, that means that pink blue has some charges. So maybe the pink ones are positive, and the blue ones are negative. So aqueous is definitely the toughest of the situations because we have this other decision that has to be made, that being, how am I going to draw this in the aqueous state? So aqueous can go one of two places. It can go here, or it can go there. So that's the usefulness of these little pieces. They tell you if I have to draw a picture of what's going on, how am I going to represent these different things? Next page. Courtesy of all the nice sparkles on your paper here, our hydrogen atoms didn't show up very well, so we're going to have to draw those back in. This is the same picture that was on the front of your balancing chemical equations thing that you just finished. The hydrogens didn't show up because they're white, but there they are. Chemistry has a law of conservation of mass. We've kind of alluded to the law of conservation of mass in the past. It says in any chemical or physical process, mass is neither created nor destroyed. It's kind of a symbolic representation of what we've been doing since the very, very beginning of this class. It basically says the sum total of the mass in the beginning and the sum total of the mass in the end have got to be the same. We've learned to interpret this in a couple different ways. We've learned to do a particle level interpretation of this. And that was just kind of a counting thing. I've got carbon atoms, I've got hydrogen atoms, I've got oxygen atoms. And in the beginning, I have one carbon atom. It's the black one in the middle. 1, 2, 3, 4. I have 4 hydrogen atoms. Oxygen atoms are red. 1, 2, 3, 4. So there's 4 of those. And in the end, black carbon atoms, I have 1. Hydrogens, 1, 2, 3, 4. Oxygens, 1, 2, 3, 4. And so that's how we've made the law of conservation of mass sort of work. And that's how we followed it. We've made sure that we have the same number and same type of particle on each side. Then we added a thought process to it that actually included the notion of mass. And that was at the macroscopic level, what did things weigh? And so we added up the parts and pieces. The mass of a CH4 particle plus the mass of 2 O particles. And if you added that up, you'd find out that that weighs 84.071 AMU. And we did that using our periodic table. And then we checked to the other side, and we added up the mass of 2 H2Os and a CO2. And said that those two masses were equal to one another. Now, realistically, we're not going to weigh it in AMUs. The little green balances weigh in grams. So realistically, if we needed to check this at the truly macroscopic level in lab, we would weigh it, and we would find out it weighed X grams. And if we let it all happen in a closed container so we didn't lose anything, it would still weigh X grams in the end. And so now all we need to do is figure out how are we going to do this without having to draw all these pictures. For now, we're going to leave the hints for balancing blank, because until we have some experience, the hints aren't really going to be all that meaningful to you. So we're going to leave that blank and come back to it. And we're going to flip to the other side here. And we're going to work on a strategy for how to balance these things without having to use particle level pictures. So how can we do this without all the little circles? Here is our new strategy. We're going to start by making a list of everything that's present in our chemical equation. So over here, we have hydrogens, iodines, and oxygens. And we're going to make the same list in the same order on the other side. And it's very advantageous to have it in the same order on both sides. And then you're going to take account of how many of each atom you currently have. So starting over here, I've got 1 hydrogen, 1 iodine, and 3 oxygens. On the other side, I'm just going to read left to right. 2 iodines, 5 oxygens, 2 hydrogens, and another oxygen for a grand total of 6. So instead of drawing all the little pictures, I'm just going to interpret the chemical formulas as imagining how many atoms are actually there. And then I'm going to start adding more of things until I have an equal number on both sides. But instead of drawing pictures and adding more, I'm just going to add more by adding more of the chemical formula. I'm basically going to stack chemical formulas up above here until I have the same number of each type of atom present. So it looks like I need more stuff on this side. The only thing on this side is HIO3s, so I'm going to add one more of them. So there's a second HIO3. And when you add something, you're going to recount. So since I added something over there, I'm going to cross those out. And let's count again. Hydrogens, 1, 2. Iodines, 1, 2. Oxygens, 3, 6. And that's it. In a delightful situation, I now have the same number and same type of atom on each side. All I have to do is write a nice, neat, tidy, cleaned up version of my balanced equation where I say how many of each I have in my stack. So my stack has 2 HIO3s to form an I2O5 and an H2O. There's my balanced chemical equation. So I've accomplished the same thing that you accomplished by drawing all the little circles. I've just accomplished it with a little less drawing. Now the question did come up, can we do this with ionic compounds? Sure. Here's one that's got some ionic compounds in it. So we start out with a list. List all the elements present. So I've got calciums, nitrogens, oxygens, aluminums, sulfurs, and some more oxygens, but we're going to count those oxygens up with all the rest of them. And then I've got calciums, nitrogens, oxygens, aluminums, and sulfurs on the other side. Keep those lists in the same order. It will make your life a lot easier if they're in the same order. And now we start counting. This compound has 1 calcium. The 2 distributes into the parentheses, so the 2 distributes in there to the nitrogen. And 2 times 3 for oxygens. There's a 6. My next compound has 2 aluminums. The 3 distributes into the sulfur. 3 times 4 is 12 oxygens, so in addition to the original 6 oxygens, I've got 12 more for a grand total of 18 of those. Jumping to the other side, we have some calcium, we have 1 of those, a sulfur, 1 of those, 4 oxygens, aluminum, I've got 1, nitrogen, this 3 distributes in, so I have 3 of those, and the 3 distributes in here to give me 9 more oxygens in addition to the 4 that I originally had, landing me at 13. All right, now we have to start trying to fix things. Here's my advice. When you start out, go after something easy. The oxygen is not going to be easy to fix. Don't start there. Oxygen is all over the place. It's not going to be obvious what we need to do to fix the problem, so don't go there first. Pick something easy, like I think I can fix the aluminums pretty easily. I have 2 here. I would like to have 2 here. All it takes is another one of that. I can fix that. Oh, yeah, 3. There we go. Okay, I add something, I have to recount. Okay, so do the counting again. We've got calcium for 1, sulfur for 1, oxygen for 4, aluminum 1, 2. Nitrogen, the 3 distributes in, so I have 3 here, 3 more below. I'm up to 6. Oxygen's the 3 distributes in, so I have 9 of them here and 9 more there. That's 18 more. I'm up to 22. I sure am glad I'm not trying to draw a picture of this. Yeah. I can't fix it. It's network issues that there's nothing I can do anything about. All right, so I fixed that. I don't know why I wrote S. That's a 1. Okay, sulfur. I feel like that's a pretty easy fix too. I have 1 of them here, 3 of them here. I could use 3 of them over here. So I'm going to make my stack be 3 tall. CaSO4, CaSO4. Every time you change something, you recount. Okay, calciums. 1, 2, 3. Sulfurs. 1, 2, 3. Oxygens. 4, 8, 12 there. Aluminums. 1, 2. Nitrogens, the 3 is distributing in. 3, 6. Oxygens, 9 here and 9 more is 18. I'm up to 30. All right, so now I fixed the aluminum and the sulfur, but now the calcium, which used to be just fine, is not just fine anymore. Balancing equations is like cleaning your closet. Sometimes things just have to get worse before they get better. And we're kind of at the it got worse stage. The oxygen we've overshot. The calcium used to be okay, but it's not okay. But we just sort of keep at it. So I need 3 calciums over here. I'm going to make this stack taller. And when I add more, I have to recount. Okay, calciums, 1, 2, 3. Nitrogens, the 2 is distributing in, so we really have 2, 4, 6 on the nitrogens. Oxygens, 2 times 3 is 6, so I have 6, 12, 18 at that stage of the game. Aluminums, I have 2. The 3 distributes in, so sulfurs, I have 3. 3 times 4 is 12, for a grand total of 30. And I've made it. Everything matches up on both sides. So now we just have to count our stacks and write our balanced chemical equation. This is a stack that's 3 tall. So I have 3 CaNO3 2 plus Al2 SO4 3 yields 1, 2, 3. So I've got a 3 tall stack over here. 1, 2, I got 2 Al NO3 3. There's my balanced chemical equation. So that's going to be the alternative to drawing all the little circles. We're going to use their symbolic representation to make more of them instead of using their particle level representation to make more of them. So at this point, we're just going to do some practicing here. So every group, go grab a whiteboard, bring it back to your table.